Give us some introduction to this very exciting field of quantum singularity.
Okay, so I would like to thank Professor Wei Dongran for the invitation, and actually it's my first time to Korea, in particular to the beautiful campus. So today I will talk about my joint work with another one, and Tyler Jarvis. So the title of my topic is Introduction of the Quantum Singularity Theory. So I suppose this is the first of the two talks. So the other one is left on the afternoon of Thursday. So in this talk, I will introduce some basic concepts in this theory and try to explain clearly the whole theory. And the second theory will be focused on the technical, most difficult part of the theory. So let's begin from the very simple part. So the simplest, actually every information is included in the very simple object called quasi-homogeneous polynomial, W. So what is quasi-homogeneous polynomial? W is a map from Cn to C and satisfies the following identity. Lambda n1, x1, lambda n, capital N, x capital N equals to lambda d times this polynomial. So here, n1, n, capital N, and d are positive integers. The weight of the variable xi is defined as qi, so it's ni over d. So related to this polynomial, there is a numerical invariant called the central charge. C hat W. So this is defined as the sum of 1 minus 2 qi. So now it follows the definition. So W is called non-degenerate if the following two conditions satisfy. So the first one is the choice of qi are unique. Second is W has singularity only at 0. A counterexample is W equals to xy. So in this case, the weight is not uniquely determined. So this is a counterexample. So actually, most interesting singularities belongs to this type, non-degenerate quasi-homogeneous polynomial. For example, this includes A, D, E singularity. So AN is this simple monomial. and the dn is x to n minus 1 plus xy squared for n greater or equal than 4. So E6 E7 E8 and you can compute the central charges of those polynomials. You can show all of the central charges of those singularities are equal than 1. For example, you can see E7 case. So in 7 case, the weight of x is 1 over 3, and the Qy is 2 over 9, and then you can compute it as 8 over 9. So this is a simple example. Another ingredient in this theory is the automorphism group. Of W. So this is defined as GW. It's a diagonal matrix such that this equality holds. So this is it's a finite abelian group. So this is a maximum symmetry group of W. So another definition is, so there is a special subgroup in GW is generated by J. So J is a matrix, diagonal matrix with this form: 2 pi Q1 EI 2 pi Qn. So this element, this matrix generates a subgroup, and then the subgroup G is called admissible if this subgroup is contained in G, and the G is contained in GW. So this is an admissible group related to the singularity W. Okay. Now I want to describe the basic block of the quantum singularity theory. Actually, the quantum singularity theory is COHFT in conservatory and Manning's language, cohomology of quantum cohomologic field theory. And this definition includes some parts. So one part is called you should describe the state space. And the other one is you should describe a multilinear map. So I will describe this later, but let's start from the description of state space. So here is a state space associated to a singularity. Actually, so in particular for this theory, this procedure is called Orbifold dicing. Orbifold dicing. In the language of intricate and Wafa. In one of the papers appeared in, I think, in 1902. So the procedure is like this. So firstly, we take element gamma, small gamma in capital G, and then we define the subspace Cn gamma to be the set of fixed points of gamma. So, and then we can restrict W to Cn gamma to get another polynomial W gamma. So there is a lemma. This lemma shows W gamma is also a non-degenerate polynomial, quasi-homogeneous polynomial in Cn gamma. And then we can define the sector, the gamma sector. So actually, the gamma sector is the space of Lefschetz simples related to the polynomial W gamma. So this is a middle dimension relative cohomology. And then take the G invariant part. So what does this homology group contain? So this group contains the following geometric objects called Lefschetz simple. So this means take the invariant part. For example, we can perturb W gamma a little bit, such that W gamma is a most holomorphic function. And then it has some finitely many non-degenerate critical points in this space. And we can take the Lefschetz simple. It looks like in this way. So if this is W gamma, this one. So if this is a critical point, and this is a corresponding critical value, and then we take a line parallel to the x-axis, goes to the minus infinity. And then we look at the pre-image. So you get something like this. So this object is called Lefschetz simple. And the boundary of this one is called vanishing cycle. So why it's called vanishing cycle is when this cycle approaches the critical point, it will vanish to one point, to the critical point. And actually the homology class is the set of Lefschetz simple. In the case W gamma is the most holomorphic, and you can take the dual space. So the dual space can be described by some differential forms. N differential forms, middle dimensional differential forms. Differential forms. So this is a gamma sector. Gamma sector.
Example?
Right. Example is because you can see E7 case. So E7 we have two variables, C2. So I should.
Remind us the normal for E7?
Right. E7 is this one. X cubic plus xy cubic. Yeah. Right. Let's see the computation of E7. Okay. In E7 case, for example, if we take the element J is a special element in this group, then the J sector is considered of only one element. So this is a trivial one. Actually, it's a function. This is a function. Function 1, it's constant function. And then we have the other element. We can get the other one. For example, for the element gamma equals to J0. And then this consists of W xy dx dy. So this is element in this group.
So what is J0?
J0 is right.
You have J, but I don't know what
Yes.
J0 is.
Yes, J0 is just the unit element. J0, yeah. Identity, yes. Identity. So actually, here I should write down completely. So this group is generated by J, and is isomorphic to Z modulo non-Z. So is this one. And so the action is, so here I don't want to describe further the action because this take too much time.
So you mean there is no other symmetry besides this symmetry for this polynomial?
The maximal symmetry is just this cyclic group, yeah. And so actually it's so this element acts on the differential forms. act on these differential forms. So the action is I can write down here. So if we denote cosine as e 2 pi I over 9, and then Jx.
Differential form on what?
On this space, on this the space of fixed points. Yeah. So if gamma is unity, so this is just C2.
Okay.
Yeah, this is C2, and then you have this form, and the action is in this way, defined as cosine cubic and cosine square x xy. So this is action element of this action acts on the variables. So you can show this is invariant by the G action.
Okay. I mean, you think this is relative cohomology, right? So that would be like some differential form which.
Right. And here, so.
What's the difference? So this is a differential form on C2. Which
Right.
Is C2? Yeah.
So here, the group G acts on the middle dimensional cohomology group, right? So then we have a G action, and then we take the G invariant part of this group. So we get this sector. But for E7 we have 9. We have 9 group elements, right? So we have 9 sectors. Each sector contains the G invariant part. Yeah. So this gives you the element in the state space.
So besides the identity element, it's just constant.
So you have G0 to G8. Yeah.
Okay. Yeah.
Yes. So for each one you have.
J0 just means J to the power 0.
Right. J to the 0 power. Okay. Because this is a matrix. Okay.
Right.
Yeah. Okay. So. So the state space is the total state space is this one, H W G. Actually, this is related to the admissible group. But in most cases, we can take G equals to the maximum switch group, GW. So this is the sum of all the gamma sector. So this is the reason why this is called the orbifoldizing. So it is orbifold by this finite group. Yeah, this is the state space. And then we have the grading. State space.
So H gamma would be what you call H gamma G over here, right?
Yes.
Okay.
Yes. H gamma G. Gamma G. So elements gamma can be written in this form: E 2 pi I theta gamma 1 e to the 2 pi I theta gamma capital N, and we require all the theta is in this interval. In this interval, and then we can define the degree shifting number. Eta gamma. So this is defined as the sum of set I gamma minus Qi. And so we can define the degree of element alpha. So this is defined of the degree of the form of alpha plus 2 times eta gamma, 2 times the degree shifting number. So we get this degree.
So what is alpha again?
Alpha is the element in H gamma.
Okay.
Yeah. So we just abbreviate G, capital G. So
is that trivial or non-trivial to show this is representable by this kind of differential form?
this is actually non-trivial, but it's a
Right.
classical.
Right. I see.
Yeah,
So
classical
this is a
story.
precise statement. It's saying this relative cohomology is the same as what kind of differential form? Is holomorphic differential form?
Yes, yes. So actually, this this cohomology can be defined as a homomorphism of the. Can be defined as a dual of this group, homology group.
Right.
Yeah, but the dual can be represented by differential forms.
So the pairing would be integration?
Right. The pairing is integration, but yeah, the pairing is an integration. But this integration, right? This is integration over here.
The left is simple?
Left is simple. Yeah. Of course, here there is a very subtle place, because the integration needs a convergence in the infinite part place. Yeah, but this doesn't influence the pairing between two differential forms. The pairing between two differential forms can be represented by the residue of the corresponding polynomial. For example, you can consider this one, dx1, dxn. So you have actually what we care about is the pairing of two differential forms.
Why do we care about that?
Because this is a metric of this state space. Yeah, but this one, but I will tell you later. Then you can understand this. Yeah. So let's finish description of the gradient. Now the proposition says the gradient respects the definition of degree. So for any gamma in GW, we have eta gamma plus eta gamma minus equals to C hat W minus n gamma. So n gamma is the dimension of the space of fixed points. And the C hat W is the central charge of W. So this is the relation. So this relation tells you if alpha is in the gamma sector and the beta in the gamma inverse sector, then the degree of alpha plus degree of beta equals to 2 times C W hat. So this is something like Poincare pairing. Yeah, respect the gradient. And the second is the unit of the state space. Actually, the unit is just the constant function. So it's contained in HG. So this is the unit. And here degree is 0. Second pairing or metric of this space. So the pairing is actually induced by the intersection pairing. So the intersection pairing is defined as the intersection of two Lefschetz simples. So one is from this side to the minus infinity, and the other one is from this side to the infinite place. So this is the intersection of two relative cycles, cocycles. And so this intersection pairing will induce the pairing in the dual space. In dual space. Okay, so now I can answer a question about the question of the pairing. So here, so this is a pure formal definition, right? But this pairing can be described in two different ways. So one way is you can take a differential form. Take a differential form in this space. For example, f dx1 dxn gamma g dx1 dxn gamma, and then define the pairing as the integration of the two forms. So here, actually, this pairing is the integration. But here, we need much words to explain what is the integration of the two differential forms, because this integration is over complete non-compact space. So you should consider the convergence in the infinite place. So what is the convergence in the infinite place? Actually, here we should time another function, exponential function, such that those forms can be convergent in the infinite place. But here I don't want to describe the detail. But there is another one to describe the pairing. So this is a residue pairing. So this is equals to the residue pairing. Residue pairing at 0. So the residue pairing is defined in this way. So this is defined as residue at x equal to 0, fg x1, xn over partial w over partial x1 times w over partial xn. So this is the definition. So then we get the state space, the pairing, the unit of the cohomological field theory. And here, of course, residue, yeah, basic notion. Right, so this is the Cauchy integration formula. Yeah, in this way is because you have n, so you just consider this one. Xn equals. So polydisk integrate all along the boundary, and this one. This is integration. Yeah.
Actually, why those partial derivatives non-zero on this?
You mean this one?
Mm-hmm.
Yeah. So actually, 0 is a unique critical point of this of W. Yeah.
Right.
So and then you integrate along a cycle.
Mm-hmm.
Along the yeah.
But 0 is the critical point of the W.
Right. Critical point.
Right.
Yeah.
But so that means the derivative is not 0.
Derivative is 0. That means
Yeah, I mean the nearby derivative is non-zero.
right. Nearby is non-zero.
Right,
Yeah.
but some of them can be 0, right? So if you take the product, then do you mean they are all non-zero, or some of them is non-zero, or I mean, do you do with that, or it's always non-zero on this? Integration?
Right. Always non-zero. Always non-zero. Yeah.
So is that-
Because you can't, because this is analytical function. You can't vanish along hierarchical dimension line. Yeah.
Hmm? I'm sorry. You mean? No, I'm just wondering why
Yeah.
it's non-zero on that torus.
Right. This can be proved. This can be proved. Yeah.
Can you prove?
I mean, yes.
What do you
Yes.
mean go around what?
Right. This you can.
No, it's equal to 0
no.
along a hypersurface. Okay. How do you go around the hypersurface? Always, I do not understand.
You can take a generic. You can take a generic n cycle. So maybe this I can ask you.
I think I understand.
Yeah.
So it's not the. I think it's probably not the xi is equal to epsilon. It's the partial derivative of w with respect to xi equal to 0, the norm. Because that's.
Then it's reasonable. Yeah.
Hmm?
Yes.
That's
Yes.
probably
Yes.
what you-
Yes.
Yeah,
Right.
That's-
Not this one. Yeah.
Not that one. Yeah.
Right.
I see.
That's.
Yeah.
Mm.
Yeah, that's very reasonable because
Yeah.
that's actually what I meant.
Okay. Okay. Yeah. So actually, when we compute it, we don't use the original definition. We use another way.
But this basic notion we need
right,
to tell students the
right,
definition.
right. Yeah. Okay. So another proposition is the pairing is compatible with the gradient. So what does this mean? This means the pairing does not vanish only for this case. So here, A is an index such that there is an element gamma such that the degree is just A. And so only in this case, the pairing does not vanish. So this is like a Poincare pairing of two differential forms over a compact manifold, right? So if three dimensional, you just have non-vanishing pairing between one dimension and two dimensional differential forms. Okay, so here I described the state space unit and the metric space. And then comes the most difficult part, the definition of a multilinear map. So this map, to define this map, we need to study the modular space. Okay, so we should study the modular space of W curves. W curves. So we have the very basic modular space. Modular space of curves. So this is the set of smooth curves. With genus G and the K market points. So this looks like in this way. K market points. And then we have the compactification. So this is the Deligne-Manifold. Compactification. Such that this modular space becomes orbifold, smooth orbifold of dimension 3G minus 3 plus K. So this is a geometrical language of the Deligne-Manifold space. Yeah, so the orbifold means you can imagine it as a manifold, but it's not a manifold because locally it should divide the action of finite group. Yeah, so locally it lacks Cn modular the action of a finite group. So this is the definition of orbifold. Of course, you have to describe the intersection part of two charts. And then I want to study the modular space of W curves. But before that, I describe modular space of R-spin curves. So this case corresponds to the polynomial AR case, AR minus 1. That means W equals to X to R. So this space is originally studied by Huijun in about 1902, I think, 92 in his paper. He wants to generalize his Huijun conjecture. So what is the element in this modular space? So the element is the isomorphism class of R-spin curves. So what is R-spin curves? So R-spin curves are algebraic curve with a line boundary over itself, such that there is a isomorphism between two line boundaries from the power LR to the canonical boundary. Yeah. So this one you can imagine as generated locally by DZ. Of course, this definition gives you a restriction of degree of the line boundary. So this means you require the degree restriction. R times the degree of the line boundary L equals to this one. Of course, you can allow the existence of marked points on sigma. So you can study this line boundary with k marked points, such that the isomorphism has such form. The tensor product of L isomorphic to k sigma tensor with k divisor boundary P1. Okay. So of course here also gives you a degree restriction. So sorry, yeah, this should be I. Writing this way. So mi are integers, are given integers. And then we have to, because here we talk about smooth curve and the line boundaries on the smooth curves. But if you want to do compactification, you have to study the degeneracy behavior of this object. So you can see this curve degenerates along a small circle, along this circle. So you can imagine this as a line boundary. So for the underlying curve, this will degenerate to a node curve. Yeah. But the question is, the line boundary will also degenerate. So at this point, this is not a line boundary again, but it becomes a Orbifold line boundary. So in this way, you get a Orbifold line boundary over Orbifold curve. Orbifold over Orbifold. So this process makes you believe that if you want to compactify this space, you should consider Orbifold with Orbifold line boundary. not only the smooth curve with the general line boundaries. So here, the information is preserved in this course. The monodromy of this line boundary along this circle becomes, in this case, becomes orbifold structure of line boundary. So monodromy here becomes a local group of these orbifold points. Because monodromy is giving you a monodromy means give you a group action. So we get a finite group P. So this finite group can be proved contained in this symmetry group G, and this group is isomorphic to a cyclic group. To this one. So in the course of compactification, the orbifold structure occur. So actually, there are two types degeneracy behavior. Two type degenerates. So one is called the Riemann case, and another is called Navier-Schwarz. But in our latest version, we will change the notation to narrow and broad because of the protest of physicists. So physicists then think our usage of the two words is not compatible with the usual language. Yeah. So they suggest us to change to broad and narrow. So we will use those two words in the latest version. But anyway, here we talk about the Riemann and Navier-Schwarz. So Riemann here means this group is trivial. Is a trivial group. Is trivial group. Navier-Schwarz means this group is not trivial. Is not trivial. That means we have the real monodromy behavior along the circle. So this type, this two type has very different behavior in the construction of the whole theory. Yeah, actually we spent much energy to deal with Riemann case. So this case is closely related to the analysis of the equation. Yeah.
Which equation? Did you write down the equation?
No, because that equation is related to the construction of virtual cycle. Yeah, I have not mentioned the virtual cycle here, but soon we will come to that. And then the modular space is this one. the isomorphism class of the curve and the line boundary P1, Pk. And here, the line boundary should satisfy the condition. So this is defined as K sigma, tensor with divisor boundaries. So here we have different notation to here, because here this is the original definition of Huijun. But then we found this is more suitable here. Here we use sigma is orbicurve, and the non-trivial points are those market points. So near the market points we have the orbifold structure. That means we have the action of local group on the line boundaries.
What's the difference? I mean, this is different from Huijun's original.
Yes, because Huijun, in his original paper, he only considered the smooth curve, and then he emergent. He has a compactification. Yeah. And so in some very rough way, he can construct the virtual cycle using his equation. But here we have actually a serious mathematical problem. So the first problem is you have to compactify the modular space of smooth curves. Yeah. So this compactification was done by our cooperator, Tyler Jarvis. So he was the first one to compactify this space. But the interesting thing is he didn't know any concepts from Orbifold theory when he wrote his original paper. And then he met Professor Yongbin Ran. And they two talked to each other, and Ran told him the compactification should be the compactification of orbicurves, orbifold structure. And then we have the right setting here.
So did he get the right compactification?
Right. He used concepts. He used some construction from algebraic geometry, some different, complicated concepts to describe that. But those concepts are equivalent to the orbifold action. Yeah. Yeah. So here are orbifold. So what does orbifold mean? If we write the local coordinates of this section as z, w. So z is the coordinate of sigma, w is the coordinate of the line boundary. Then the action is like in this way. Z, and then e 2 pi I p w. So this is the local action of the local group. So what is this? What does this space look like? This space is a branched covering of the modular space of smooth curves. So we have the stabilization map from this one to this fundamental modular space. Just forgetting all the orbifold structure and the line boundaries, and you get this one. Here I forgot to mention one point.
So here is action, right? Local action.
Local action, yes.
So what do you mean by orbifold?
Yeah, orbifold.